for example. And then for energy as well, you can demand that the potential U1 minus potential U0 should be less than, let's say, a millirydberg. And you can change those criteria. You can relax them to let the calculation converge faster, or you can make them more strict when you have a solution and you really want to test the stability of that solution. Typically, that's when you make them stricter. And of course, you can add more criteria to this. Later today, I believe Professor Mazin is going to tell you about magnetic calculations. So if you want to do magnetic calculations, you can also add magnetic moment as another criteria of convergence. You calculate the magnetic moment on each site. And let's say if you have a spin 3/2 system, you expect a, say, G times spin 3/2 total magnetic moment. And then you can look at that magnetic moment. And when you reach the magnetic moment that you expect for a spin 3/2 atom, then you can basically stop the calculation. Now, if the criteria of convergence are met, you're happy. If they're not met, which means that if you start with a should guess at U0, you calculate the wave function, you use those wave functions to find a new potential, and you notice that there is a noticeable change in the potentials between the successive iterations of the calculation. If there is such a difference, then you use that potential, plug it back into the equation, and you solve it to get a new wave function. And then you use that new wave function to calculate the next level of potential. And then you look at the criteria of convergence again, and then you go in this loop until your criteria are satisfied. So basically, that's the way almost all of these codes work. The devil is in the detail here, and how different codes basically work. And we try to get into some of the methodology that's used for the calculations. Now, before we see the methods, let me show you how important it is to choose the proper U to begin with. For example, this is a simple calculation for the vanadium. It's one of the transition metals. I believe there is a picture of a periodic table in the conference room, and you can see where vanadium is. So you have in the transition metal series, you have scandium, titanium, vanadium. So it's the third in the the third transition metal in the series, and therefore you can write its electronic configuration as 4s2 3d3. So it has 3 electrons in the d shell. So overall, it has 5 valence electrons. But you can redistribute those as 4s1 3d4. So you take one of the electrons from the s orbital into the d orbitals. And when you do that, the interactions between the electrons change, because the interactions between d orbitals are different from the interactions between the s orbitals. And that simply comes from the fact that the d orbitals have this sort of butterfly shape, as you've seen in your quantum mechanics course, and s orbitals are spherically symmetric. And also their spatial distribution, how far they go out, how far they reach from the nucleus into the interstitial space is also different. Typically, the interactions between the d electrons are stronger, quite stronger than the s electrons. The s and p electrons, you can imagine them as nearly not interacting, whereas the d electrons are strongly interacting. And therefore, when you start with a different guess at the potential or the starting point for your electron distribution, the solution of DFT is going to be very different. Look at these two plots. They have some common features, but the actual energies, the places where the bands cross, they certainly differ, right? And that tells you the importance of selecting the proper U. And there are algorithms to select the proper U. These are called the functionals. And based on the choice of functionals, you can actually get different solutions. For example, your group may do a calculation and get a band structure for some new material that Jean-Pierre made, for example, and then another group would do the calculation on the same material, and it's the same material, it comes from the same group, but these two different theory groups may actually get different DFT results for them. And eventually, the test of which calculation is correct I would say, is up to experimental data. Eventually, you have to compare, for example, the band structure from these two groups to the ARPES data that Jean-Pierre and collaborators obtained, and then they can say, well, this calculation seems more reasonable than the other. I'm kind of advertising for the experimentalists here, but this is this is a talk by an experimentalist. Now, here is, I need to distinguish between two different, basically two different type of electronic states in solid, and those are the valence bands and the core levels. So let me, these words are used quite a lot by the DFT community. So let me quickly explain the problem. In DFT, you're trying to calculate the electronic wave function across the entire solid. But the solid, of course, is made of this periodic array of ions. And now you put yourself in an electron's position. When the electron is moving in the space between two ions represented by these black points, when the electron is traveling in the distance between them, it is nearly free indeed, and it doesn't see much of a potential really. But when it goes into the region that is close, or let's say in the vicinity of an ion or of a nucleus, then it sees the atomic potential, which is very strong. And therefore, the electron takes the form of atomic orbitals. So the kind of the wiggly lines that I draw here are meant to represent the atomic orbitals. I believe in your solid state course, you have also learned about the so-called tight binding model. The idea of a tight binding model in a nutshell is that if you have a periodic array of atoms in a lattice and you want to look at how the wave functions change, what you do is that you know that at every site you have atomic orbitals, and you know those are s orbitals, p, d, f orbitals. But if you put them in a periodic lattice, these orbitals will interact. And the way that they interact is represented by a bunch of integrals. For example, this alpha integral tells you the interaction between the, say, orbital wave function at position r and at position r minus capital R, where the capital R is the Bravais lattice. So it basically represents the overlap between orbital wave functions. These are called, therefore, overlap integrals. These overlap integrals change the energetics of the electrons at the core level. And so eventually what you end up getting at the core level is going to be not exactly the atomic orbitals, but a linear combination of atomic orbitals. Those functions are sometimes referred to as the Wannier functions. And when you write the block state for the system, it turns out as e to the ikr, as you expect from the block theorem, times an amplitude, and that amplitude is going to be basically these Wannier orbitals. It's going to be a linear combination of atomic orbitals. And eventually it looks like this. So here is basically those atomic orbitals, some linear combination of them, and they're modulated by an e to the ikr, which is the sinusoidal wave function. And that represents the propagation of the core states with a wave vector k. So if you look at an atom in general, this is typically in Ashcroft and Merman, this is the nomenclature that you have. You have a nucleus at the very center of the atom. Then you have the core electrons that are bound to the nucleus very strongly. And then you have the valence electrons. And everything I told you so far was about the core electrons. The tight binding approach works best for the core electrons because they're tightly bound to the nucleus. They basically obey the distribution of atomic orbitals. Going back to the example that I showed you before, in vanadium, for example, these orbitals, 4s2 and 3d3, these are the valence shell. These are the outermost shell. But let's say 1s2, 2s2, 2p6, 3s2, 3p6, all of those electrons, you can put them in the core. And you can deal with them nicely and reliably using the tight binding approach or a linear combination of atomic orbitals, because they're, to begin with, they're pretty much confined within the core region inside the lattice. Now, the challenge is to deal with the valence electrons. The valence electrons are the outermost electrons, and they are gonna truly extend into the region between these, the sort of the atomic regions. We call it the interstitial region in the context of a solid. Now, to deal with these the valence band wave functions, to obtain the valence band functions, of course, what we learned in solid state courses is mainly nearly free electron approach and independent electron approach. But these approaches, as I said, work quite okay for completely non-interacting systems. But as soon as you have a little bit of electron interaction, then they in fact fail. Or they will give you an inaccurate description of the band structure. And the reason is that these potentials are not so weak, in fact. The electron, even though, as I said in the beginning of my talk, electrons obey Pauli exclusion principle and they try to avoid each other as much as they can, but eventually they do interact. They're forced to be inside a lattice and they do interact. And because of the simple fact that the electrostatic Coulomb repulsion is such a strong potential, even obeying the Pauli exclusion principle, the electrons still have a substantial interaction. And you can simply approximate it. So the Fourier transform of the potential is given by 1 over the volume of the of your system, an integral over the unit cell of the e to the ikr times a sum over all Bravais lattices. This is basically an average over the entire lattice of whatever electrostatic potential you have at each site. And let's take that potential to be simply 1 over r Coulomb potential. And when you do this integral, you're gonna get, so this is a 1 over r potential for the electrostatic Coulomb repulsion. What you get is something like e squared over k squared. And then you can just sort of manipulate this formula a little bit using the Bohr radius, and you can write it in terms of e squared over 2a naught times some other factors. And remember, this e squared over 2a naught, this is the Rydberg, and Rydberg is 13.6 electron volt. This is basically the binding energy of electrons in an atom, and it's of the order of tens of electron volt. And so these electrostatic potentials come to be around tens of electron volts in a simple approximation. So they can be very strong indeed. And that's why, in order to calculate the valence bands, you cannot keep using the independent and nearly free approximation forever. You have to do better at some point. And again, that's the job of computational techniques. Now, generally speaking, as I said, you have these two things. You have the core levels and you have the valence levels. The core levels basically obey the atomic orbital behavior. The valence levels, when they are in the interstitial region, the region between the atoms, they basically act as plane waves, e to the ikr. It's very simple. But when they reach the core region, they have to take the shape of atomic orbitals because they're entering the atomic space and they fall into the atomic potential. And basically, you have to always satisfy the Schrodinger equation. And here in this core region, the Schrodinger equation has a U, and the U has the shape of an atomic potential. So these electrons change their form and they become oscillatory. And the reason why they become oscillatory is because the atomic orbitals, remember, they are oscillatory because the atomic orbitals have high energies. And remember, the higher the energy, the more wiggly the wave function will be. You basically, as you increase the energy, you increase in the shape of the wave function, you increase the number of nodes. You, in a very simple way, if you look at two wave functions and one of them has more nodes or fluctuates more between positive and negative, that represents a higher energy state. Again, in your quantum mechanics, you've learned how to relate the quantum numbers to the number of nodes. Let's say psi n Lm, the total number of radial nodes is going to be n minus L minus 1. And as you increase these quantum numbers, you increase the number of nodes and you increase the energy. Okay, so the wave functions become wiggly in this core region and they become smooth in the interstitial region. And this behavior needs to be captured by by basically the density functional theory. Another important behavior that needs to be captured by density functional theory is to make sure that the valence electron wave function is orthogonal to the core states. So remember, these are two parts of your solution, and these two parts should be independent from each other, and they should be orthogonal to each other. And so therefore, what happens is that if here I'm plotting the core levels, so the core levels are atomic orbitals or a linear combination thereof, modulated by e to the ik dot r. These are the core bands. Now, if I plot the valence band, they look kind of similar but different in the sense that the valence bands have also these wiggles in the core region, but their oscillatory pattern is different from the oscillatory patterns of the core levels. And in fact, it's not just any pattern. It has to be selected in such a way that this integral would vanish. The oscillations of the valence states should be such that when you multiply them by the oscillations of the core states, the pluses and the minuses in this integrand eventually will go to zero. And of course, nature takes care of that by itself, but computationally, when we want to do it, we have to build in these properties into the wave functions. And again, it's very hard to do all of this by hand, so hence the advantage of computational methods. So once again, just to show you, this is the interstitial region. This is where the core levels are basically zero and the valence level are non-zero. In fact, in the interstitial region, this integral holds very easily because in the interstitial region, the core levels are basically, they don't exist. The core levels are restricted to the core region. And when you go to the interstitial in this yellow region, you see the core levels basically go to zero, but the valence electrons have a finite amplitude, of course, right? So the multiplication of these two goes to zero in a trivial manner. But in the core region, things are more complicated. The core levels are oscillatory, the valence levels are oscillatory, and now you have to choose the shape of these valence bands such that these oscillations cancel each other eventually. And in order to do this, in order to basically find the proper shape for the lattice wave functions and make sure that the valence states are orthogonal to the core states and they have the right energies, you use there are various methods for calculation of this valence band with DFT. These methods are called cellular augmented plane waves, orthogonal plane waves, and pseudopotential methods. They all were published in Physical Review, somehow all of them in the same journal. The first one is in 1933 by Wigner and Seitz, whom you know from the Wigner-Seitz unit cell. The next one was by Slater, from the Slater determinant, basically, 1937. The next one was by Herring in 1940, and the next one was by Phillips and Kleinman in 1959. And of course, these methods have not stopped since 60s. They have been developed and they have been changed. And today there are even new methods, but even today we use these methods at the core. A lot of DFT calculations are based on these methods. Now I know that I'm condensing maybe a lot of information in this session, but the goal of this quote-unquote tutorial is to give you an overview on the topic. I'll try to introduce all these methods. I apologize if the pace may be a little bit too fast, but I'm happy to answer your questions maybe at the lunchtime or something. Jean-Pierre, feel free if you want to have another Zoom call or something, I'm more than happy to come online and answer these questions on a one-to-one basis in whatever form that you want. It just seems that unfortunately I cannot hear you very well if you ask questions from the conference room. So I'm available the whole day. So feel free to just let me know if you want to talk. Now, okay, so let us start by the cellular method. Now, the cellular method, as the name, as you can tell from the name, it has to do with the unit cell. It has to do with basically confining your calculation to a single unit cell. And there are some approximations that you have to make when you do that. You're trying to solve the structure of a lattice. The cellular method tells you that there is a way to do that fairly reliably by confining most of your work to one unit cell. This method was, in fact, as I said, it was started by Wigner and Seitz in 1933. And what they wanted to do as a sort of one of the first serious attempt at computational methods in solid state physics was to calculate the Fermi surface of sodium. That was one of the first things they wanted to do. And basically, they started from the block function. So they said, okay, but it's a lattice. The wave function should be periodic and it should follow the block theorem. In addition to that, they said, well, if we want to solve the Schrodinger equation, we can solve it in one unit cell, hence the name cellular method. And we, for simplicity, we choose that unit cell, let's call it C0. It's the 0th unit cell, and we choose that unit cell to be centered at the origin, at the Brevet lattice equals 0, right at the origin of your coordinate frames. And then, because your potential is periodic, and you have a second order differential equation, the Schrodinger equation, you have some simple boundary conditions. You basically need to satisfy the continuity of the wave function and the continuity of its gradient as you cross the boundaries of the unit cell from one unit cell to the other. And so they basically said, we're going to use the block states. We're going to solve the Schrodinger equation in one unit cell. And across that unit cell, we impose these two boundary conditions. The first one is the continuity of the state of the wave function within it has a block state, a block type. It's a block type state, of course, so it is periodic. And so they said we want this periodic wave function to be continuous, and basically the normal so the normal component of its gradient has to also be continuous. So this little n vector here is showing the normal to a Wigner-Seitz unit cell, and basically the normal component of your gradient has to be well behaved, has to be continuous. Now this is the phase center cubic unit cell of sodium. Remember, sodium is phase center cubic, and this is the Wigner-Seitz unit cell of sodium. And again, just a reminder, the Wigner-Seitz unit cell was, you learned it in your solid state course. In order to make a Wigner-Seitz unit cell, you take one atom in the lattice, and then you connect it to all the neighboring atoms, and then you draw planes that are the perpendicular bisectors of those lines. And then you let these planes intersect with each other, and the volume that they enclose is called the Wigner-Seitz unit cell. It is usually the best method in terms of preserving the symmetries of a problem to create a unit cell. Remember, unit cells are not unique by no means. You can define unit cells in many different ways. The Wigner-Seitz unit cell is one way of defining the unit cell, but it turns out to be one of the most, both computationally and analytically, really one of perhaps the best way of defining the unit cell. Now, there are two approximations in the cellular method. The first approximation is in the cellular method by Wigner and Seitz, was to change the potential, the real potential inside that unit cell, say C0, from whatever symmetry it has to a spherically symmetric potential. Now, this is, of course, a gross approximation. So let's say you have a hexagonal unit cell, right? And you have atoms at every corner of that unit cell and one atom at the center. They simply replace this to the left with this to the right. They said, well, we're going to just simplify things. We only take spherically symmetric potentials. We try to change the amplitude of this potential so that it follows the amplitudes that are in the unit cell, but the symmetry should be spherical. And the reason for that is that they basically, at the time, they knew how to solve Schrodinger equation for atoms. And so what Wigner and Seitz wanted to do, I believe, was to solve the Schrodinger equation for a unit cell. And so what they did is that they took the unit cell as an atom, and then they impose a simple spherically symmetric potential, just like you have in atoms. You have a nucleus at the center, and the Coulomb potential of the nucleus exerted on electrons is a spherically symmetric 1 over r potential, basically. And so they knew how to solve that problem. Here is basically the radial form of the Schrodinger equation. You've seen it in your quantum mechanics. It's no different from solving the Schrodinger equation for hydrogen atom. It's exact same problem. And so basically they reduce this cellular calculation into a hydrogen atom calculation for simplicity. And when they do this approximation of changing or modifying the potential from, say, 6-fold symmetric to just spherically symmetric, then when they go to the spherically symmetric potential, they could also use the spherical harmonics to explain the charge distribution or the angular distribution of charge or the wave function, and they had a radial wave function. And here, what you see here is the radial equation, which is the more difficult one to solve. And of course, they can solve that for specific energy for every band, and they can get the band structure. So now the second approximation, so that was the first approximation. The first approximation was to treat the unit cell like an atom, basically, and make the potential spherically symmetric. And then you can, then they knew how to use the Schrodinger equation. The second approximation was that, well, even if you do that, the total wave function has to be given by some sum over a finite number of spherical harmonics and the radial wave functions with an amplitude that I represent here by A sub Lm. So now this sum, of course, can have many terms, but Wigner and Seitz said that another approximation that you can make based on how accurate you want the final result to be is to truncate this sum and only choose maybe the first 2 or 3 terms that are important and relevant. And this was really just to save on computational times. And basically you can just, you can approximate it by, for example, choosing 3 terms in this sum and then 3 boundary conditions. For example, let's say the wave function be continuous across, let's say, this face, but maybe not this face, and its derivative be continuous across, for example, this face and this face. Now, of course, the choice of which boundary condition the choice of which boundary condition to use and how many terms you pick in this wave function is not at all trivial. That's a very difficult choice. But anyways, you have to do that in order to simplify the calculation and in order to reduce the computational cost of the calculation. Nevertheless, you choose, for example, say 5 terms in this sum, and you choose 5 different boundary conditions. Let's say orthogonal continuity of the derivative on 3 surfaces and continuity of the wave function on 2 surfaces, for example. And then you construct a 5 by 5, an n by n, based on how many boundary conditions you pick and how many terms you pick. Then you get an n by n characteristic equation, and then you solve the system of equations computationally. And from there, you can get your electronic states and therefore your band structure. Now, here is kind of the result that they had. So this is just to summarize. In the cellular method, you have the Wigner-Seitz unit cell. This is for sodium. So you have an FCC Wigner-Seitz unit cell. The first thing you do is that you approximate this complex unit cell with a spherical unit cell. So just make it very simple. You make a unit cell that has a radius called R0, such that the volume of this sphere, 4/3 pi R0 cubed, the volume of this sphere would be the same as the volume of this Wigner-Seitz unit cell. So you translate it to this sphere. That would take care of your boundary conditions, because now you only have 1 orthogonal component, right? Because this is completely symmetric. And you just need to have the continuity of the wave function and the continuity of the let's say its derivative across this one surface. So you really simplify the problem. You take the potential to be spherically symmetric. And in fact, in their case, they basically had only 1 boundary condition. The boundary condition was to have the derivative of the wave function to go to 0 as it crosses this sphere, which means that the wave function kind of becomes flat as it crosses the boundary of that sphere. And so the problem becomes extremely simplified in the cellular method. You see the unit cell becomes a sphere, and the potential becomes spherically symmetric. So literally, the unit cell becomes a hydrogen atom at that point. And they solved it. And here is the wave function that you see for their calculation. For the cellular method, the wave function is shown as a solid line. Notice that the solid line has two nodes. It's positive, goes to negative, and then goes back to positive. And then eventually it flattens out. And that makes sense because in this region, this is radius away from the nucleus in units of Bohr radius. A naught is the Bohr radius. When you're within the core region, you have some oscillation in the wave function. The dashed line, if you look at the dashed line here, this is just the atomic wave function of sodium. So this is just Schrodinger equation for an atom, actually. So if you look at the atomic wave function of sodium, in the core region, the atomic wave function, which is the dashed line, and the band structure calculation, which is the solid line, they are almost identical. But once you get out of the core region, the atomic wave function, which is the dashed line, kind of does a little bit more wiggle, and then eventually it goes to zero, because that is the boundary condition for atoms. Basically, the boundary condition for atoms is such that the wave function should go to zero when you go too far from the atom. When R goes to infinity, the wave function should go to zero, because the atomic wave function should be basically only sizable around the nucleus, and then it goes to zero. But the cellular wave function is very different. This is the wave function for a lattice. So here what happens is that in the core region, it mimics the atomic potential. But when it gets out of the core region, it basically flattens out, and therefore it satisfies this boundary condition that the derivative of the wave function is zero as you cross this R naught, which is the radius of the basically unit cell. So what you see is a flat plane wave basically in the interstitial region, and when it enters the atomic region, it kind of follows the atomic potential. So this was the cellular method, fairly simple, but this really was the first major breakthrough in creating the computational techniques. Now, associated with the cellular method is another concept that you definitely, if you read almost any DFT related paper, you will read this sort of cooking jargon, the muffin tin potential. And the idea of the muffin tin potential is that in order to deal with the unit cells, you simulate them as the cells inside a muffin tin. And okay, so I don't have much time left. I see only 10 minutes. All right. And so what you do basically within the cellular method is that you to simplify let me see. Okay, within the cellular method. Okay, so if the blue lines here are the atomic potentials, in the cellular method, you have a potential that looks like this. This potential is fine, but it's not ideal. It has a spherical symmetry, so it is easy to solve the problem. But notice that its derivative is discontinuous in the interstitial region. Whereas in reality, this is the kind of potential you want. You want something where the derivative basically goes to zero in the interstitial region. And this is given by the Muffin Fin approximation. The Muffin Fin approximation is shown here. The way it works is that you assume a 1/r potential and in the core region, and then the core region itself has a radius of R naught, and you can change that R naught in the calculations. And then when you reach the interstitial region, the potential simply truncates to zero. And that looks like basically like a muffin tin. So you have the atomic potential within the core region, and then when you go to the interstitial region, it just flattens out. And so your potential becomes very simple. It's zero in the interstitial, and it's atomic potential within the core region. And basically, you can use this approximation, the muffin tin approximation. You can change the radius of the muffin tin, or R naught, and you can basically refine your calculation. Now, because I have very little time left, I don't think if I can go through all of this, of course. And let me just tell you a little bit about the augmented plane wave, and then I can stop. The augmented plane wave method is another technique that was invented by Slater in 1937. This is actually today also used quite extensively. The way that this method works is to assume that the solution to the crystal Schrodinger equation is a superposition of these augmented plane waves. And these augmented plane waves shown by phi, they have several properties. They become plane waves in the interstitial region. So the interstitial region is the light orange color here. And then they are continuous at the boundary between the interstitial and the core region. And in the core region, they basically obey the atomic Schrodinger equation. So in the core region, you have atomic orbitals, or a wave function, to be accurate, a wave function that is orthogonal to the atomic orbitals, but it has more or less the same oscillations. In the interstitial region, you have a plane wave, and you stitch them together at the boundary between the interstitial and the core region. And that boundary is set by the radius of the muffin tin. And again, so all of these you can change in computations. You can decide how far your muffin tin should go and where it should stop. The final solution, basically solution to the crystal wave function is going to be a linear combination of these augmented plane waves. Let me just go through maybe something that is more important. So I think I explained all of this. Once you have these wave functions from the augmented plane wave, in order to calculate the energy of the states, which is going to be eventually your band structure, typically you use a variational method. And so what you do is that you write an energy functional, which is the Hamiltonian with kinetic energy and potential energy acting upon the wave function and normalized by the wave function. And then when you write this energy functional, then you minimize it with respect to all the coefficients in the expansion of your wave function. This is at this point, it's just the variational principle that you learn in your quantum mechanics. It's the exact same problem. Your wave function is given by a set of parameters, and you write the energy functional and minimize that energy functional with respect to those parameters. And when you do that, you get the final parameters and you get the final form of the wave function and hence the energy. And so this is the basic of the augmented plane wave method. And here I'm showing some of the calculations done early on iron, copper, and zinc. Iron is BCC, copper is FCC, zinc is hexagonal close pack. And for all of them, these calculations have worked quite well. And even today, if you do the calculation, you will get pretty much the same band structure. For the zinc specifically, notice how quadratic the bands are. They look almost like nearly independent electron approximation. And that's because zinc has nearly filled orbital shells. It has 4s2 3d10. All the shells are filled, and therefore interactions are minimal. And as a result, the calculation is really all quadratic. It looks like a nearly free electron approximation. In maybe I finish in 1 minute, Jean-Pierre. I think I'm almost done. In my group and in some other groups, we use the Wien2K. It is a code that is, I think, quite suitable for experimentalists if they want to do calculations. The workshop that Jean-Pierre talked about was on the Wien2K technique. I hope that we can have that workshop again at some point. Basically, the program has a graphical user interface, and you can initiate the calculation by giving it the lattice structure, the nearest neighbor distances. Basically, the program starts calculating the nearest neighbor distances based on the lattice structure, and it sets the muffin tin radius usually to be a bit less than half of the nearest neighbor distances. It calculates all the symmetry groups of your structure, and then it starts sort of having a first guess at the potential that it wants to use. And here, the choice of the functional is very important. Typically, we and many other groups use the PBE functional, but you can use different functionals for these calculations. you generate a K-mesh. The finer the size of your K-mesh, which is the number of K points at which you want to solve the equation, determines how fine or how accurate your final solution would be. And typically, to start the calculation, you can use maybe 1,000 K points, but then you can increase it to maybe 10,000 K points. And then you start, so the program calculates a density across your lattice, and it starts doing this augmented plane wave. So this is LAPW0. The APW stands for the augmented plane wave method. So it's a linearized augmented plane wave. And then it goes through several steps. For example, it adds orbital potentials, and it does the linearized augmented plane wave step number 1. When it solves the equation, actually, it gets for you these wave functions and the energies. Then it does the second step. In the second step, it adds up all the states and creates a new density, and then it will look for the criteria of convergence. Meanwhile, this is, so the left side here, the left branch is to calculate the valence band. The right branch is to calculate the core states. And eventually it has a mixer where it stitches together the core states and the valence states at the boundary between the core and interstitial regions. And it searches for the convergence. If it satisfies, it stops. If not, it goes back into the loop and starts iteratively calculating, modifying the potential and calculating the wave functions for you. You have to set the radius of Muffin Fin, as I said, in the program, and there are some charts about how you set that. And here I'm showing some calculations, for example, for magnesium oxide. It's an insulator, and the choice of functional can give you different solutions. This is with the PBE, or the Purdue Burke-Erzenhoff functional, and this is with MBJ, or the modified Big-Johnson functional, and there are many other functionals. But you can see that these two, the main difference between the choice of functionals is that the band gap is different between, for example, the PBE calculation and the excuse me, MBJ calculation. And of course, you can compare those to experimental data eventually. For example, you can do optical measurements and measure the band gap and see which one of these is more appropriate. I stop here. There's not enough time to go through the rest. The orthogonalized plane wave and pseudo-potential methods. Originally, there was a plan that maybe the talk would be 2 hours, which is why I made it a bit longer. Jean-Pierre, I'm done. I'll be happy to come back online whenever the students want, if they need to have more discussions.
Okay, well, thank you. So, Fazel, try to take a few questions. Can you hear me?
I can hear you, not very well, but please go ahead.
Okay, maybe I'll type them if people have questions and you can answer. Any other questions?
Are there any situations where like any of these methods would be absolutely like not acceptable?
Yeah, very good question indeed. Well, I would say I can't say if they're absolutely not acceptable, but I would say that as the interactions in a solid become stronger and stronger, you need to question the robustness of calculation more and more. Because remember that at the end of the day, these calculations, the challenge in these calculations are specifically when you have to deal with correlated metals, I would say. Because in metals, you're facing a kind of a situation that's quite tricky. On one hand, you have the core states that are localized. And then on the other hand, you have the interstitial states that are the valence bands that are delocalized. And you have to solve these two and kind of match their wave functions. And in a very simple way, you can assume that you have e to the ikr in the interstitial region, which is the plane wave, non-interacting. And then you have atomic orbitals that are very oscillatory in the core states, right? But you can, imagine that it's going to be extremely difficult to create the oscillations in the core region if you just superpose a bunch of plane waves. You can almost never do that, right? So, which is why you have to have the solution for core states separately, and then the interstitial or the valence electrons separately, and then somehow make the two meet at the radius of the muffin tin. And this problem becomes more and more difficult when the interactions become stronger and stronger. For example, let's say if you want to calculate the, let's say, normal state of superconductors or high temperature superconductors, then you need to be really careful about your calculations, and you need to really check them with experiments, and you need to constantly ask the validity of your calculation. I would say that's where it becomes very challenging. Thank you for the good question.
Okay, Igor.
Yeah. The answer to the previous question is resoundingly no. Because the question is equivalent to asking, is there a situation where integration by part is absolutely unacceptable? What you see on your screen are mathematical methods for solving Schrödinger equation. Asking whether it's acceptable or not is basically just challenging mathematics behind. What you may ask is how useful or are there cases when approximations that use when setting up, when you apply these calculations are unacceptable? Usually no, there might be cases where they're not particularly useful, but there's no such thing as unacceptable. You make an approximation, it may be good approximation or not so good approximation. It's never hurt you to use this and see what's coming out. So I don't know, does it help?
Yeah.
Okay.
I believe that was Igor, right? How are you, Igor? Yeah, certainly. Thank you for helping to answering this question. I believe you'll see this probably in Igor's talk on the magnetic calculations. I'm sure he's gonna give you a very nice introduction to those. And maybe added to that is that DFT calculations can also provide really invaluable insight into materials. For example, I don't know if Igor will talk about this or not, but some of the work that his group has done on spin orbit mod insulators in systems that are potentially spin liquid, magnetic systems that are potentially also spin liquid. In those calculations that are also, I would say, extremely challenging, but not only they provide, say, a band structure or an understanding of the material, but they also provide invaluable insight into how to modify the materials or how to create maybe better spin liquid systems. Sometimes you need to look into the trends that come out of these DFT calculations, and as a material expert, it helps you maybe changing some energy scale, whether it's spin orbit coupling or it's certain lattice distortions. You can change those things according to DFT results, and that helps you tuning the materials. So these, the computations, I would say, in the end, are extremely insightful.
Okay, one more question or comment from Florian. Please speak clearly.
Are there any checks, like self-consistent checks you can do to ask to check are those approximations you make? Like, do they hold? Anything you can do in that sense?
Yeah, I mean, okay, yeah, certainly, very good question. Yes. So, for example, let's say for us, when we calculate, let's say a band structure of a material, you can check a few things. My take on it, so my personal take on your question is that the most important thing is to check your results with experiments at the end of the day. For example, the first thing is that you see you have an insulator, let's say, or a metal. And if you have a metal, for example, you can get the Fermi surfaces of that metal. So the Fermi surface geometry of the metal, you can calculate from these calculations. And then you know when you compute the Fermi surface of the material, you know what's the volume of the Fermi surface, and then you know how many electrons are contributing to the valence band. And also you can map the velocity of those electrons. And those quantities are the kind of things that you can experimentally measure. So there is this technique called quantum oscillations. My group and John Pierre's group do these experiments where you can literally count the number of electrons, and so therefore you can basically, with these methods, you can reconstruct the shape of the Fermi surface. And so you can rigorously check the calculations against experiments. If you're working with an insulator, of course, the band gap, I would say, is the best way to cross-check the result of DFT with experiments. And you can measure the band gap with a variety of techniques, from either transport measurements to optical measurements. And in magnetic calculations, for me, maybe the best test would be the magnetic moment on a site. And in fact, not only you can check that against, say, a measurement of magnetization experimentally, but even when you look at the criteria of convergence in your system, you can see that the magnetic moment, let's say you have an iridium atom, iridium 4+ on a site, and you expect a certain total moment for it, you will see that as you go through the iterations of the calculation, the moment starts to go up, and then eventually it reaches the full moment of whatever you expect for iridium 4+, and then it stays there. And you can check the spin moment, you can check the orbital moment separately, and these are basically the analysis that the calculation will give you. And you can check it against what you expect from basically atomic physics. Another thing to check would be the energy, the total energy of the calculation. If you only want to look at the calculation itself without, say, comparison with experiments, you can do different calculations, use different functionals, and you can see which one of them give you lower energy, for example. Another thing that you can check is that when you look at the states, when the system calculates the state, it gives you something that's called a density matrix. And that density matrix basically gives you the filling of orbitals. And then you can look at that matrix and you look at the filling of each orbital and compare it against basically your chemical intuition. For example, if you have 3 electrons in the d orbital, you should see that that matrix is block diagonalized, and you have like 3 electrons in one block and 0 in the other block, basically. So these are the outputs of the calculation, and there's plenty of those. And yeah, you use those for self-consistency checks.
Okay, so we have to wrap up. So thank you, Fazel.
Cool. Thank you.